my name is Samar, and I am thrilled to be here today to share with you about my passion for blockchain and my journey as a blockchain developer. I am excited to be here today to share my experiences and insights with you and look forward to learning from all of you as well. Thank you. My presentation about Dora Dōjō and my research on elliptic curve cryptography and public key encryption. Dora Dōjō is a fictional character from the children's animated television series, Dora the Explorer. She is known for her adventurous spirit and her ability to solve problems through critical thinking and creativity. In this project, we will explore the use of elliptic curve cryptography and public key encryption, which are two important concepts in modern cryptography. Elliptic curve cryptography is a type of cryptography that uses elliptic curves to create public and private keys. These keys can then be used to encrypt and decrypt messages, ensuring secure communication between two parties. Public key encryption, on the other hand, is a cryptographic technique that allows for the secure transmission of information over an insecure channel, using a pair of keys, a public key and a private key. The use of these techniques has become increasingly important in modern times, as more and more sensitive information is transmitted over the internet. With the rise of online shopping, online banking, and other online services, it is important to have secure communication channels that can protect against eavesdropping and other forms of cyber attacks. In this project, we will explore the underlying principles of elliptic curve cryptography and public key encryption, and demonstrate their application in real-world scenarios. We will also discuss the strengths and weaknesses of these techniques, and examine some of the current research being done in the field. Thank you for your attention, and I hope you enjoy learning about Dora Dōjō and the fascinating world of modern cryptography. Before we start, we will talk about brief of Dora Dōjō, the open-source knowledge community co-created by hackers with a keen interest in cutting-edge technologies, including encryption and Web3. The community is dedicated to sharing knowledge, and they regularly host live broadcasts, audio, and text-based sessions that cover various topics like L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. The Dora Dōjō community specializes in specific topics such as Scroll/Polygon zkEVM, Eigen's hybrid proof system, Starkware, Aztec, Optimism, Zcre, Aptus, Move, cryptography, including zero-knowledge proof, public key encryption, hash functions, and lattice ciphers, distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communication and spacecraft system design. Everyone is welcome to join the Dora Dōjō community and take part in this collaborative knowledge-sharing experience. You can contact them on TG@Dōjō, at DoraDōjō0, and claim their bounty. Moreover, they encourage you to propose any content you would like to share, and their community will fund and disseminate it globally. So, join the cutting-edge technology revolution and become a member of Dora Dōjō today. Also, don't forget to check out their bounty program on dorahasikeis.io, where you can earn rewards for contributing to the community. The Dora Dōjō team is looking forward to hearing from you and collaborating with you to advance their knowledge of cutting-edge technologies. Elliptic curve cryptography, or ECC, is a type of public key cryptography that uses elliptic curves over finite fields to perform cryptographic operations. It's known for its strong security properties and high efficiency in terms of computation time and key size. Unlike other public key cryptography algorithms, ECC is resistant to attacks by quantum computers, which makes it a popular choice for modern cryptographic applications. ECC is widely used today in a variety of applications, including SSL/TLS protocols, wireless communication, and secure messaging apps. ECC's ability to provide strong security and efficient computation make it essential for secure communication over the internet and other digital networks. As the threat landscape continues to evolve, it's important for developers and security professionals to stay up to date on the latest developments in ECC to ensure that their systems remain secure. In short, elliptic curve cryptography is a powerful tool for securing modern communications, and its importance will only continue to grow in the years to come. In the context of elliptic curve cryptography, ECC, and public key encryption, we need to address the following points. What exactly is ECC and how does it work with public key encryption? What are the reasons for the widespread use of ECC in modern cryptography? What advantages does ECC offer over traditional cryptographic methods? Elliptic curve cryptography, or ECC, is a type of public key cryptography that uses elliptic curves over finite fields to perform cryptographic operations. This may sound complicated, so let's break it down. Firstly, let's look at what public key cryptography is. In traditional cryptography, the same key is used to both encrypt and decrypt a message, meaning that the key must be shared between the sender and receiver. Public key cryptography, on the other hand, uses a pair of keys, a public key and a private key. The public key is available to anyone who wants to send a message, while the private key is kept secret by the recipient. When the sender encrypts a message using the recipient's public key, only the recipient's private key can be used to decrypt the message. So, where does ECC fit into all of this? ECC uses elliptic curves, which are mathematical objects defined by a set of points that satisfy a specific equation. These curves are used to generate the public and private keys used in public key cryptography. The use of elliptic curves over traditional methods results in smaller key sizes, which means that cryptographic operations can be performed more quickly and efficiently. Additionally, ECC is resistant to attacks by quantum computers, which are expected to become more common in the near future. This makes ECC an attractive option for modern cryptographic applications, including secure messaging apps and wireless communication. In summary, elliptic curve cryptography is a type of public key cryptography that uses elliptic curves to generate keys. It provides smaller key sizes, faster cryptographic operations, and is resistant to attacks by quantum computers. Here's an example of how to generate an ECC key pair using OpenSSL and Python. This code uses the EC module from the cryptography library to generate an ECC key pair, using the SECP384R1 elliptic curve. The OpenSSL.backend argument tells the library to use OpenSSL as the backend for generating the keys. The code then extracts the public and private keys in PEM format, which is a commonly used format for storing cryptographic keys. Finally, it prints the public and private keys to the console for demonstration purposes. Elliptic curve cryptography, or ECC, is used widely in modern cryptography due to a number of reasons. Firstly, ECC provides a higher level of security compared to other cryptographic algorithms, such as RSA or Diffie-Hellman. This is because ECC requires a larger number of operations to be performed in order to break the encryption. ECC also uses smaller key sizes, which makes it more difficult for attackers to find the correct key. Secondly, ECC is more efficient than other cryptographic algorithms. Due to the smaller key sizes, cryptographic operations using ECC can be performed more quickly and with less computational power. This makes ECC an attractive option for resource-constrained environments, such as mobile devices or IoT devices. Thirdly, ECC is resistant to attacks by quantum computers, which are expected to become more common in the near future. Quantum computers can quickly break many of the traditional cryptographic algorithms, but ECC is designed to resist such attacks. Finally, ECC is widely used in a variety of modern applications, including SSL/TLS protocols, wireless communication, and secure messaging apps. This means that there is a large community of developers and security professionals who are familiar with the technology and can provide support and guidance on its use. In summary, ECC is used widely in modern cryptography due to its high level of security, efficiency, resistance to quantum attacks, and widespread use in a variety of applications. Here's an example of how to perform an ECC encryption and decryption using the cryptography library in Python. This code generates an ECC key pair using the SECP384R1 elliptic curve, then encrypts a message using the public key and decrypts it using the private key. The code first extracts the public key in bytes format from the private key, then loads it using the load_pem_public_key method. It then uses the cipher class from the cryptography library to encrypt the message using AES in CTR mode, and the encryptor object to perform the encryption. The code then decrypts the message using the decryptor object created from the private key. Finally, it prints the encrypted and decrypted messages to the console for demonstration purposes. Elliptic curve cryptography, or ECC, offers a number of advantages over traditional cryptographic algorithms, such as RSA and Diffie-Hellman. One major advantage of ECC is its efficiency. ECC uses smaller key sizes, which makes it more computationally efficient than other cryptographic algorithms. This means that cryptographic operations using ECC can be performed more quickly and with less computational power. This makes ECC an attractive option for resource-constrained environments, such as mobile devices or IoT devices. Another advantage of ECC is its higher level of security. ECC requires a larger number of operations to be performed in order to break the encryption, which makes it more difficult for attackers to compromise the encryption. ECC also uses smaller key sizes, which makes it more difficult for attackers to find the correct key. This means that ECC provides a higher level of security compared to other cryptographic algorithms, such as RSA or Diffie-Hellman. ECC is also resistant to attacks by quantum computers, which are expected to become more common in the near future. Quantum computers can quickly break many of the traditional cryptographic algorithms, but ECC is designed to resist such attacks. Finally, ECC is widely used in a variety of modern applications, including SSL/TLS protocols, wireless communication, and secure messaging apps. This means that there is a large community of developers and security professionals who are familiar with the technology and can provide support and guidance on its use. In summary, the advantages of ECC over traditional cryptography include its efficiency, higher level of security, resistance to quantum attacks, and widespread use in a variety of modern applications. Here's an example of how to generate an ECC key pair and use it for encryption and decryption using the cryptography library in Python. His code generates an ECC key pair using the SECP384-R1 elliptic curve, then encrypts a message using the public key and decrypts it using the private key. The code first extracts the public key in bytes format from the private key, then loads it using the load_pem_public_key method. It then uses the encrypt method of the public key object to encrypt the message using the optimal asymmetric encryption padding (OAEP) algorithm with SHA-256 as the hash function. The code then decrypts the message using the decryptor object created from the private key, using the same padding algorithm as used for encryption. Finally, it prints the encrypted and decrypted messages to the console for demonstration purposes. In mathematics, an elliptic curve is a smooth, continuous curve that has a special set of algebraic properties. Specifically, it is a plane curve defined by an equation of the form y² = x³ plus x plus b, where a and b are constants, and the curve is defined over a field of characteristic not equal to 2 or 3. An elliptic curve can be graphed as a set of points in the xy plane that satisfy the above equation. Unlike other curves, an elliptic curve has a finite number of points, but the number can be very large depending on the size of the underlying field. Elliptic curves are used in cryptography to provide a mathematical structure that enables secure communication between two parties. The security of an elliptic curve cryptosystem relies on the difficulty of computing the discrete logarithm of a point on the curve. In order to use an elliptic curve for cryptography, a group structure must be defined on the set of points on the curve. This group structure is defined using an operation called point addition, which is a geometric interpretation of the addition of points on the curve. Elliptic curves have become increasingly important in modern cryptography due to their efficiency and strong security properties. They are used in a variety of applications, such as key exchange protocols, digital signatures, and encryption schemes. In summary, an elliptic curve is a smooth, continuous curve defined by an equation of the form y² = x³ plus x plus b. They have a finite number of points and are used in cryptography to provide a mathematical structure for secure communication. Here's an example of how to define and plot an elliptic curve using Python's matplotlib library. This code defines the constants a and b for the elliptic curve y squared equals x cubed plus x plus b, and defines a function curve to compute the right-hand side of the curve equation for a given x value. It then generates an array of x values over a range, and computes the corresponding y values for each x value using the curve function and the sqrt function from the number.py library. Finally, it plots the positive and negative branches of the curve using the plot function from the matplotlib library, and adds axis labels, a title, and a legend before displaying the plot. This code can be used to visualize the shape of an elliptic curve defined by a specific set of constants a and b. In mathematics, an elliptic curve is a curve defined by an equation of the form y squared equals x cubed plus x plus b, where a and b are constants, and the curve is defined over a field of characteristic not equal to 2 or 3. The equation is called the Weierstrass equation, named after the German mathematician Karl Weierstrass who introduced it in the mid-19th century. The equation is used to define points on the curve, where both x and y are in the same field. For example, if the curve is defined over the real numbers, then x and y are real numbers. If the curve is defined over a finite field, then x and y are elements of that field. The Weierstrass equation defines a smooth, continuous curve that has some interesting properties. One property is that it is symmetric about the x-axis, so if a point x, y lies on the curve, then so does the point x, y. Another property is that the curve has a finite number of points, but the number can be very large depending on the size of the underlying field. The constants a and b have an effect on the shape of the curve. For example, if a is negative and b is positive, the curve will have a distinctive Hess shape. If a is positive and b is negative, the curve will have a Hooke's shape. Elliptic curves are used in cryptography to provide a mathematical structure that enables secure communication between two parties. The security of an elliptic curve cryptosystem relies on the difficulty of computing the discrete logarithm of a point on the curve. In summary, the equation of an elliptic curve is y squared equals x cubed plus x plus b, where a and b are constants and the curve is defined over a field of characteristic not equal to 2 or 3. The equation is used to define points on the curve, and the constants a and b affect the shape of the curve. Elliptic curves have important applications in cryptography due to their efficiency and strong security properties. Here's an example script in Python that demonstrates the equation of an elliptic curve. In this script, we define a class called elliptic curve that takes two parameters a and b as inputs, which represent the coefficients of the equation of the elliptic curve. The __str___ method of the class returns a string representation of the equation of the elliptic curve in the form y squared equals x cubed plus x plus b. The is_point_on_curve method checks if a given point x, y, is on the curve by plugging in the values of x and y into the equation of the curve and verifying that the equation holds. We will move to talk about key generations. Here's an example script in Python that demonstrates how to generate a private key using elliptic curve cryptography (ECC) for use in public key encryption. We first import the necessary modules: random for generating random numbers, hashlib for hashing the private key, and cryptography for working with ECC. The generate_private_key function uses the EC module to choose an elliptic curve. In this example, we use the widely used SECP256R1 curve, generates a random private key using that curve, serializes the private key as a PEM-encoded string, and hashes the PEM-encoded private key using SHA-256. Finally, the function returns both the private key object and its SHA-256 hash. Here's an example of how to use this script to generate a private key. It will output the generated private key object as well as the SHA-256 hash of the private key. Note that this is just an example, and in practice, you should always use a secure random number generator and a strong hash function when generating private keys for use in ECC-based public key encryption. Here's an example script in Python that demonstrates how to generate a public key using elliptic curve cryptography (ECC) for use in public key encryption. We first import the necessary modules, random for generating random numbers, and cryptography for working with ECC. The generate_public_key function takes a private key object as input, gets the elliptic curve used to generate the private key, generates the public key from the private key, serializes the public key as a bytes object, and returns both the serialized public key and the curve used to generate it. Here's an example of how to use this script to generate a public key from a previously generated private key. When you run this script, it will output the generated public key object. Note that this is just an example, and in practice, you should always use a secure random number generator and a strong elliptic curve when generating private keys, and their corresponding public keys for use in ECC-based public key encryption. Here's an example script in Python that demonstrates how to perform point multiplication on an elliptic curve. We first import the necessary modules, random for generating random numbers, and cryptography for working with ECC. The point_multiplication function takes a private key object and an input point as inputs. It first generates the public key from the private key and gets the elliptic curve used to generate the private key. It then converts the input point to a point object using the EC elliptic curve public numbers class. Next, it multiplies the point object by the private key using the multiply method of the elliptic curve public key class to get a new point. Finally, it returns the coordinates of the new point. Here's an example of how to use this script to perform point multiplication on the SCCP-256R1 elliptic curve. When you run this script, it will output the coordinates of the new point resulting from the point multiplication. Note that this is just an example, and in practice, you should always use a secure random number generator and a strong elliptic. Then, I want to move to talk about two important concepts in cryptography: encryption and decryption. Specifically, I will discuss how they are used in elliptic curve cryptography, ECC, and public key encryption. Encryption is the process of converting plain text into a secret code, which can only be read by someone who has the key to decrypt it. It is used to protect data from being accessed by unauthorized users. In ECC, encryption is done using a public key, which is derived from an elliptic curve equation. The sender encrypts the message using the recipient's public key, and the recipient uses their private key to decrypt it. Decryption, on the other hand, is the process of converting the secret code back into plain text. It requires a key that is only known by the recipient, who can use it to unlock the encrypted message. In ECC, decryption is done using a private key, which is generated from the same elliptic curve equation used to derive the public key. Public key encryption is another important concept in cryptography. It is a type of encryption where a public key is used to encrypt data, and a private key is used to decrypt it. This allows anyone to send encrypted messages to a recipient, without needing to share a secret key beforehand. The recipient can simply use their private key to decrypt the message. In ECC, public key encryption is also used for secure communication. The public key is derived from an elliptic curve equation, and is used to encrypt the message. The recipient then uses their private key, generated from the same elliptic curve equation, to decrypt it. In conclusion, encryption and decryption are essential concepts in cryptography, and are used extensively in elliptic curve cryptography and public key encryption. These techniques provide a secure way to protect data and ensure that only authorized users can access it. The encryption process using elliptic curve cryptography, ECC. Encryption is a fundamental concept in cryptography that is used to protect data from unauthorized access. ECC is a popular technique for encryption because it offers a higher level of security compared to traditional encryption methods. The encryption process using ECC involves three main steps. Step 1. Key generation. The first step is to generate a pair of keys, a private key and a public key. The private key is kept secret by the owner, while the public key is shared with anyone who needs to send an encrypted message. The keys are generated using the properties of an elliptic curve equation, which makes it difficult for an attacker to derive the private key from the public key. Step 2. Message encryption. Once the keys have been generated, the sender can encrypt the message using the recipient's public key. This is done by converting the message into an elliptic curve point and then adding the public key to it. The result is another point on the same curve, which represents the encrypted message. This process is called point multiplication, and it makes it very difficult for an attacker to decrypt the message without the private key. Step 3. Message decryption. When the encrypted message is received, the recipient can decrypt it using their private key. This is done by subtracting their private key from the encrypted point on the elliptic curve, which results in the original message point. The message point can then be converted back into plain text. In conclusion, encryption using elliptic curve cryptography is a powerful technique for securing data. It involves generating a pair of keys, encrypting the message using the recipient's public key, and then decrypting the message using the private key. This process provides a high level of security that is difficult to breach, making it an ideal choice for many applications. Here's an example code in Python for encryption and decryption using elliptic curve cryptography, ACC. In this example, we first generate a key pair using the elliptic curve SECP256R1. We then convert the public key to bytes so that it can be shared with the sender. Next, we define the message to be encrypted, and use the encrypt method of the public key to encrypt the message. We use the OAEP padding scheme with SHA-256 as the hashing algorithm. Finally, we use the decrypt method of the private key to decrypt the message. We use the same OAEP padding scheme with SHA-256 as the hashing algorithm. When we run the code, we will see the encrypted message and the decrypted message printed to the console. I want to discuss some of the key applications of public key encryption. Public key encryption is a technique for securing data that is widely used in many different applications. Here are some of the most important applications. First, let's talk about digital signatures. Digital signatures are used to provide a way for people to prove that a message or document was created by them, and has not been tampered with since it was signed. Public key encryption is used in digital signatures because it provides a way for people to verify that the signature was created by the person who claims to have signed it. Digital signatures are used in many applications, including online contracts, financial transactions, and legal documents. Second, let's talk about key exchange protocols. Key exchange protocols are used to establish secure communication channels between two parties who have never communicated before. Public key encryption is used in key exchange protocols because it provides a way for the parties to exchange encryption keys without having to share them over an unsecured channel. Key exchange protocols are used in many applications, including secure email, instant messaging, and virtual private networks. Finally, let's talk about the SSL/TLS protocol. The SSL/TLS protocol is used to secure web communications between a web browser and a web server. Public key encryption is used in the SSL/TLS protocol because it provides a way for the web server to prove its identity to the web browser and to encrypt data sent between the two parties. The SSL/TLS protocol is used in many applications, including online shopping, banking, and other sensitive transactions. In conclusion, public key encryption is a powerful technique for securing data. It has many applications, including digital signatures, key exchange protocols, and the SSL/TLS protocol. These applications provide a high level of security that is difficult to breach, making public key encryption an ideal choice for many different types of applications. I want to take a moment to thank you all for attending my presentation on elliptic curve cryptography and public key encryption. I hope that you found the information that I presented to be informative and valuable. As we discussed, elliptic curve cryptography and public key encryption are powerful techniques for securing data. They have many applications in a variety of industries, including finance, healthcare, and e-commerce. By using these techniques, we can ensure that our data is secure and that our online transactions are protected. I also hope that I was able to answer any questions that you had about these topics. If you have any further questions or would like more information, please do not hesitate to reach out to me. Once again, thank you for attending my presentation. I appreciate your time and attention, and I hope that you found it to be a valuable learning experience. Thank you.